Here we have today Nicolás Pérez. He's an assistant professor in the Department of Earth and Environmental Sciences at Weber State University. Previously, he was a postdoctoral fellowship. Previously, he had a postdoctoral fellowship at MIT, and he was a doctoral student at Syracuse University. He's a geomorphologist and conducts multidisciplinary research at the nexus between Earth's surface processes, climate, and biodiversity. In his research, he uses a combination of fieldwork, analytical data, including geochron, thermochron data, geomorphic and climatic information from hydrological stations and remote sensing sources, and incorporates that with numerical modeling. He's interested in questions such as how precipitation rates, rock fractures, and tectonic uplift rates influence erosion in mountain ranges, or how past changes in paleoclimate may have affected river incision. You're doing a lot. I like the big picture scope, personally. Outside of geology, Nicolás enjoys reading, running, sharing time with friends and family, cooking, and riding his bike. So welcome, Nicolás, and we look forward to your talk.
Thank you, everybody, for taking the time to attend this talk. It is a pleasure to be here in this event from the Utah Geological Association, and also to get to know the grounds of the Utah Geological Survey. I have started meeting some of the people that work here. I have invited some of you already to some lectures in my classes at Weber State, and I hope to, especially this summer, once all the chaos from classes ends, get to know more of you and maybe go to the field, get to know some of the facilities, the core facilities. There's so much that you guys do for the state, and I want to learn more from you guys. So yes, as I was introduced, I'm a professor at Weber State, and I have been there for the past 4 semesters. I actually have a couple of students that I have taught, Ethan here, who got the scholarship, and that makes us pretty proud, and Tara back there, who is now working for the Utah Geological Survey, also an outstanding students, both of them, and Ethan is actually on the picture on the right with a different look. But yeah, so at Weber State, we have undergraduate only students, no graduate program, so we focus a lot on undergraduate research and also on undergraduate teaching and mentoring for students. So it's a little bit different than other universities, but we all play a role, an important role in the education of the future Utah workforce. So right now we're going through so many changes and budget cuts and things, but I believe that we all play a role in telling the general public how important geology, geosciences are for Utah and for the country. Many things, mining, so many things that Utah needs geologists and the workforce, and these relatively smaller programs spread throughout Utah allow a lot of people that don't have the means to go to another state and that need to keep working while they attend university to get an education. So all the schools in Utah are important, and I think we need to protect them all. Okay, so now going back to the talk, I changed the title a little bit, and I heard some people commenting. You may have seen the word ontogeny on my talk. So here I kind of changed it a little bit. So relationships between orogen ages, the age at which a mountain and orogen is created, the rates of erosion of these mountain ranges, and the erodibility, or how easy it is to erode the rocks in that place. And I used the word ontogeny when I was an undergraduate student. I liked reading Stephen Jay Gould a lot, and I remember seeing this term, and it basically is a term used in biology and paleontology and relates to the changes, the morphological changes through which an organism goes through its lifetime. And what I will try to show you today is that mountain ranges also go through ontogeny changes, and those affect the erosion stages at different points in the life of a mountain. I would like to thank my collaborators from different institutions who have helped me in different parts of this research. So why are we interested in studying erosion? some of you are erosion experts in this room, but erosion affects landscapes around the world in many ways. Here you're seeing an image of a landslide in Highway 1 in the coast of California. This is an image that may repeat every few years or even every year in parts of this highway, where erosion processes like mass wasting processes affect infrastructure, close or cause the closure of highways for months and even years. This also happens in places like my home country, Colombia. This is a landslide that damaged the road from the capital, Bogota, to the lowlands in the eastern part of the country, a region that has a lot of oil industry. So it's quite an important road. And every year we have road closures for days or months because of these mass wasting processes. And some of the events are more catastrophic. This is another mass wasting process that occurred in the Amazonian front range of Colombia, a very wet region. So after a period of high rainfall during several days, we had large debris flows. You can see the size of some of those granite clasts that came rushing and destroyed a whole neighborhood. So seeing this as I grew up and as I was an undergraduate student, I have been very interested in studying erosion processes, and not always related to human infrastructure, but to larger scale, big picture problems also. And apart from causing a lot of trouble, erosion also creates some of the most magical landscapes on Earth, and part of them are here in this western part of the US. This is a picture that I took in Grand Canyon in Arizona. This past weekend, we were looking at incision in the Colorado River near Moab, a place called Gold Bar, where you can actually see gravel terraces that show you how the Colorado River has been incising into the Colorado Plateau through time. So Utah is a great location to study erosion and incision. Here's another picture from volcanic landscape in Colombia, and how this river, the Juanambu River, has cut through these flat-lying volcanic rocks and creating this amazing landscape. And when I talk about erosion, I refer to the removal of solid material from the Earth's surface due to chemical and physical processes. So basically, all the material that is being shed from the surface of the Earth. And as geoscientists, we usually measure erosion in different units. Typically, we refer to as a unit of length over time, because we're looking at how fast the surface is getting lowered over time. So we talk about meters per year or meters per million years. So you will see those numbers in my talk. You can also quantify it as volumes. If you have a sedimentary basin or a lake where the sediments are going, you can quantify how much volume of sediment is removed over units of time. So these are just ways in which we measure erosion. And one of the cool things that you can do with data of erosion rates is that you can create maps of erosion rates, like the one that you're seeing on the lower left of the image, which is showing you hotspots of erosion in yellow color, and then places with lower erosion rates in blue. And in order to be able to make these maps that are very useful for other people, like people that study maybe where a landslide might get triggered, they would maybe focus on those yellow areas and see what's going on there. You usually go to smaller watersheds, like the ones shown on the upper right image, and you collect erosion rates for those smaller watersheds. And people then make correlations between the erosion rates measured at these smaller watersheds and then topographic data or climatic data from each of these watersheds. And then with those relationships, they extrapolate to the rest of the landscape. And then we can bring the structural geologists to try to explain to us why we are getting these bands of high erosion in some places, how do these relate to maybe faults that maybe in this region and things like that. One of the big questions that scientists are still working on is what causes higher erosion rates in some places than others. And we have a pretty good idea, but we're still publishing each year. Some people say that previous paleoclimatic conditions may have triggered high erosion rates, for example, in the Quaternary. Other people think that tectonic activity is the major player in these discussions. And we're getting to a point where we have the computer capacity to create these large-scale computer models that can reproduce erosion throughout Earth. So this is an image from a paper by Sals et al. In 2023, and they basically reconstructed the erosion rates on Earth for the past 100 million years. So they took these relatively artistic paleogeographic and paleoelevation maps that have been created, and then they said, okay, if the topography is changing this way, what is the expected erosion that these mountain building processes and erosion of mountain ranges is causing, and where is this sediment going? And then with the model outputs, you can compare to actual sedimentary basins near the margins of the continents and see if these models are able to reproduce those erosion rates and sedimentation rates. So is it mainly driven by processes of mountain building? And one of the things that I think this study that I'm going to show you is important is because the equations that we're using in these models, so you have an equation that says erosion equals something. And so you have some parameters. And so it depends on how steep the landscape is, how much precipitation there is. But sometimes we have to use a lot of constants in these equations. And I'm going to show you that there are some aspects of erodibility, how easy it is to erode sediment or soil from a mountain range that relate to how old that mountain range is. And so we need to start thinking of a time component of some of these parameters that go into the equations. But I think it's an exciting time for geomorphology. In general, it is well known that tectonically active areas have high erosion rates. And here I have mostly compressional settings, but places like extensional settings like the basin and range also have high erosion rates. Usually places that have had recent tectonic activity have steep landscapes, and these steep landscapes have high erosion rates. So if you compare two areas, one that has a high uplift rate, mountains are growing, and then one that has low uplift rate, mountains are not growing so fast, the higher erosion rates are going to be in that green high uplift rate mountain range. And the reason is that the high uplift rates are creating a steeper topography, and steeper topography creates landscapes that are easier to erode. So that's kind of relatively easy for us to think about, and remember that typical physics problems that we have where we have a block on a ramp, and then if we change the angle, we make the block slide easier. And the reason is that you're increasing that weight component that is pointing down slope. So if I give you a hose and I give you these three settings and I ask you to remove that pile of gravel or sand, it's going to be easier to remove it from your driveway in the steeper slope. And the way in which geomorphologists look at that is that they collect erosion rate data from landscapes with different steepness or catchments within a mountain range with different steepness. And usually you find a relatively well-behaved system. This is a schematic, but you usually have here erosion rate on the y-axis and steepness or gradient on the x-axis, and you find this positive correlation. So steeper landscapes give us higher erosion rates. So again, this is something that we can relate easily with some basic physics law. But wait a minute. So in a cool paper in 2007, Molnar said, like, wait a minute, how come that there are steep landscapes, like places like maybe the Appalachian Mountains or the Sri Lanka Mountains, the Western Ghats in India, and so some parts in the Craton of South America that are quite steep, yet when you measure erosion rates in these areas by any means, you get really low erosion rates. And you can see this problem in this graph, where again, I'm showing you the erosion rate on the y-axis and the steepness of these catchments where the data was collected on the x-axis. And for a value of high steepness, there is orders of magnitude difference between the Himalaya, an active mountain range, and Sri Lanka, an inactive mountain, an inactive landscape. So there is something that steepness alone cannot explain. And here are some pictures of some of these landscapes. These are steep cliffs in the Guyana Shield with low erosion rates in South America. This is a place called Salto del Ángel, the jump of the angel, or Roraima. And these are some of the steep mountains in Sri Lanka that have low erosion rates. So how do we explain this problem? And the answer is that there are other important factors apart from just slope that are affecting erosion rates. So here is a relatively simple equation where you have erosion rate on the left, and then the parameters that control erosion rate on the right. So you have a letter K, that is rock erodibility. You have the precipitation rate or discharge, how much water there is in the system, and then there is the slope. So all these three things affect how much erosion you get for an area. And you might have high in one and low in the other, so they might balance. And these vary across landscapes and places depending on these three variables. And when I say rock erodibility, I refer to the rock strength, that depends on the lithology, the fracture density, and things like that. So in this same paper, Molnar et al. In 2007 said that, okay, slope doesn't seem to be the main control in some areas. The main variable actually is how weak or erodible the rocks are, so that K purple variable that I showed you. And he showed that fracturing of rocks during tectonic deformation, here showed in a compressional setting, but also can be in an extensional setting or strike slip, will weaken the rocks. So if you fracture a quartzite into smaller pieces, for example, you're making it more erodible. It's easier to pick it up. And again, I can give you the similar experimental setting, but changing you the grain size or the amount of fracturing of rocks, and ask you to wash away those that sediment, and it will be easier to wash the pile of sand or smaller material on the top. So that's how erodibility can affect landscapes. It's not the same to have pretty strong rocks compared to highly fractured rocks. So maybe what we're seeing in this type of graphs is that the Sri Lanka data, the orange data, is from a tectonically inactive area that doesn't have a lot of fractured or hasn't been fractured since the Jurassic. And then if we are in the Himalaya, we have rocks that are actively being fractured, have fresh fractures, and are more easily erodible. So for the same value of steepness on the x-axis, if you go up, you have order of magnitude differences in erosion, and maybe that's the reason. And since this 2007 paper, there are lots of papers, even some by colleagues here in the Wasatch Mountains, showing that erodibility matters. And this is a cool paper by Neely et al. From mountains in California associated to the formation of the San Andreas Fault. And this study went to two areas that have very similar rocks, but with different fracture densities. The San Gabriel Mountains in blue on the left have higher fracture densities, and therefore we expect higher erodibility. The San Jacinto Mountains on the right have lower fracture densities and therefore lower erodibility. We would expect it would be harder to erode a rock. And when they plot their erosion rate data from different catchments spanning several gradients in steepness across these mountain ranges, they find these data. So they can kind of separate the two mountain ranges in two different relationships. The northern San Jacinto Mountains plot lower than the San Gabriel Mountains in erosion rate and steepness on the x-axis. And the idea is that if you follow that yellow line, so for the same erosion rate, the mountains in the northern San Jacinto Mountains have to be a lot steeper. So for the same erosion rate, they have to be steeper than the mountains in the San Gabriel Mountains. So something that is harder needs to steepen or be much steeper to erode at the same rate than something that is very weak. Or the other way to look at it is if you take the same steepness, the rocks that are harder will have a lower erosion rate for that value of steepness. They cannot erode as much compared to the other mountains that are highly fractured. And that's an interesting relationship. So looking at these type of studies made us think about whether there might be erodibility changes throughout the lifespan or ontogeny of an orogen. So as we change from being actively deformed, crushed in this active tectonic deformation to an inactive orogen, can we see changes in erodibility? So we're going to have less fractures. We're going to have fractures that are not actively being connected. Can we see changes in erodibility? When tectonic activity is shut off in a mountain range, we will still have uplift rates. So we will still have some uplift, but it's mostly going to be controlled by isostasy. So if we remove some weight due to erosion, there's going to be some isostatic uplift. So even places that are tectonically inactive will continue to erode through time due to this isostatic component. And as an orogen is being eroded, even without tectonically active deformation, so if you start with a crustal column that looks like this in an orogen and you shut off tectonics, the idea is that you will start eroding first through the highly fractured rocks, and then you will get to rocks that haven't been deformed having undergone brittle deformation through time. So let's say that we have active deformation and then we shut off tectonics in that area. Over time, this is what we expect in a schematic way to happen. We're going to be eroding through highly erodible rocks first, and slowly we're going to bring up deeper, harder rocks, even without tectonic activity. So in this case, over time, we would be decreasing the erodibility or increasing how hard it is to erode those rocks. Easy to erode, hard to erode. And another thing that happens over time is that fractures, if they're not actively being connected, they might be healed by processes such as mineral precipitation, which might aid to give some strength to those rocks over time. So if we compare that original paper comparing two areas in a similar geographic region that have different fracture densities with our hypothesis of temporal changes in erodibility, this is kind of the hypothesis that we would expect, that if we plot data for erosion rate and steepness for different catchments in young orogens or old orogens, we should find this a separation in between the relationships, maybe. So the young orogen would plot higher and the old orogen would plot lower. This is because the erodibility is higher for the young orogen. So for the same steepness value, there would be a lot more erosion happening in the young, highly fractured orogen. So we looked for a place where we can test these hypotheses, and as it happens in the US, we have orogens of several ages, some areas that are tectonically active and some areas that are tectonically inactive. And we use this map from the USGS that has been reviewed over time, but it was published by Feneman. And we have, again, younger orogens on the left and older orogens on the right. So we use these general subdivisions for our data, and then we compiled and used previously published data of cosmogenic nucleates. That is a type of data that is used to measure erosion rates at a catchment scale. So here's the data that we're using, all those points throughout the US in different orogens or different tectonic provinces that have different age of orogeny. And what is this cosmogenic nucleate data? These are basically erosion rates that were obtained from collecting river sand from different rivers throughout North America, and then studying the chemistry of these of the quartz in the sands from these rivers. And how this works is that the Earth surface is constantly being bombarded by cosmic rays, as you can see in the diagram on the left. And when some of these high energy particles hit atoms of oxygen in quartz, for example, it can also be in other minerals, they transform that atom of oxygen in another element, and commonly in beryllium. And there is not a lot of beryllium in rocks otherwise, so it's generally produced by these type of reactions. So we can measure the amount of beryllium that there is in quartz derived from catchments in different parts of the US. And this has been done by different researchers in the past 30 years. So we are using their data basically. And the idea is that if you think of the diagram on the right, there is 3 different stages. So time is increasing to the right. And this is one relatively stable surface that is being bombarded by these cosmic rays and high energy particles. And over time, the soil or quartz in the soil is going to get a higher concentration of this beryllium compared to a young soil. So if we measure the concentration, it tells us something about how long that soil has been exposed to the cosmic rays, or how much time it has been accumulating this beryllium. And now we can also think about how it relates to erosion rates. So when you have high erosion rates, you're going to be basically exposing new soil and new quartz grains that have not been exposed to the surface. They're kind of new grains. So your sample will look a lot like this. And if you have low erosion rates, areas like the Appalachian Mountains where you have low erosion rates, your soil sample or sand sample is going to look more like the one on the right. It has a lot of beryllium. It has had a lot of time to accumulate this cosmogenically produced beryllium. And so we basically, instead of sampling soils, we take samples of sand, which are basically grains that were washed from soils throughout the catchment, and that gives us an average over all these outcrops that would take us a lot of money and time to collect. So basically, each data point that you saw on the previous map is a value of erosion rates, 10 meters per million year, or you can put it in millimeters per year. Another one will be 300, another one would be 1,000. And it comes from one catchment, one small drainage in in a different part of the country. So now we have erosion rates. We can use GIS to extract topographic data, and so get the slope of the landscape or how steep the rivers are in that area. And then we can associate it to a different orogen. So we have really nice information for all these points. And here is the first hypothesis of what we could expect. We could see that slope is the main control of erosion rates throughout North America. And so if this is true, this is synthetic data, but this is kind of what we would expect. If we compare different areas, in this case, I'm showing the Appalachian Mountains, the Rocky Mountains, and the Pacific coast mountain ranges, the coast of California. And if the steepness is what it's controlling the erosion rates here, or the most important factor, we would expect this relatively positive correlation between erosion and basin steepness, and areas that are tectonically active, like the western part of North America, should plot higher in this graph compared to the Appalachian Mountains that are tectonically dead and also have less steepness. Another hypothesis would be that we do have, for each province, a relationship between erosion rate and steepness, but when we compare between different origins of different ages, we have another factor affecting that relationship. So that factor is basically displacing these lines on the vertical axis. And this would be the erodibility. So if the age of the origin, how young it is, means that it is more erodible, then we would expect this separation on the vertical axis. So for a similar value of steepness, you would find large order of magnitude changes in erosion rates. So not just one single relationship, but several. And we started, before using the data, we decided to do some modeling, so landscape evolution modeling, to test this hypothesis. So what is the effect of erodibility changes on erosion rates? And to do this, we created, in a computer model, an orogeny or mountain range that was 4 kilometers high, so a pretty big mountain range, and we shut off any tectonic activity or imposed rock uplift. So we just let it erode, and then any rock uplift that occurs is due to isostasy. So over time, the topography is gonna get lowered, but it doesn't occur as fast as without isostasy, but we have some rebound. So slowly, like the Appalachian Mountains, they are getting eroded slowly over time. And we run the model for 100 million years. And we tested two conditions. In one, the mountains have the same rock type, the same fracture density, so the same erodibility through 100 million years. And in the second one, we are decreasing the erodibility. So every time we are, as the mountain is getting eroded, it's also harder to erode those rocks, like we would expect from changes in the fracture density due to less tectonic activity. And here are the results from these models. So again, on the y-axis, we have erosion rate, and on the x-axis, in this case, I'm showing channel steepness, but it's basically a metric of how steep the landscape is. And we can see that for a constant erodibility, we see one single relationship, no matter the age of the origin. But if we change to a variable erodibility, we see this displacement on the y-axis. So for the same value of steepness of the landscape, we have huge changes in erodibility. The younger origin erodes much faster for that same steepness. Yeah, I can use that. Thank you.
Thank you.
So now we can look at our results. So again, I'm going to show you on the y-axis the erosion rate, and on the x-axis the gradient or steepness of the landscape. And this is the result for the different provinces in the US. So we have on the upper left, the Pacific border, and then on the lower right, the Appalachian Mountains. So in general, what you can see is that there is a positive relationship between erosion rate and steepness of these catchments, although there's some scatter in those graphs. And when you plot them together, this is what you see. So here I'm just showing the Pacific border mountain ranges, the Basin and Range, and the Appalachian Highlands. So 3 of these origins. And on the right side, I'm just showing you the regression lines. So what we're seeing here is that for a single value, if you go along that yellow line, one value of steepness, you have order of magnitude changes in erosion rates, similar to what we were showing in the second hypothesis. And here is all the data. And again, on the right side, just the regressions for each of these provinces. And again, you can see that the lines are displaced vertically instead of just following one single tight relationship of erosion rate with steepness. So similar, several changes, large changes vertically if we go through the same steepness. So how do we explain these data? Again, one possibility is that they are showing just they are just related to the modern rates of uplift. And so we have higher rates of uplift on the west and lower rates on the right. But if this was the case, we would expect that only that relationship. And what we're seeing looks more like the second hypothesis, where we have this vertical separation, and maybe we have changes in erodibility among these different provinces or origins. Now, I haven't talked about the age of these origins or provinces, but if we look at something like the median age of orogenesis for each of these provinces, and this is something that is hard to calculate, but we did our best here. If you plot on the x-axis the median age of orogenesis, so how old these mountains or these origins are, and then on the y-axis, I'm plotting the erosion rate at the mean basin steepness. So I took this value of steepness and I got the erosion rate that this line intersects. And you can see that the younger origins here on the right have the highest rate of erosion for a given steepness. So if all the basins in the US had the same steepness, if all the mountains were equally as high and steep, the mountains on the western younger mountain ranges would be eroding faster. So we're basically kind of taking the effect of slope from the landscape and looking at, if we take away that effect of landscape steepness, how fast are these provinces actually eroding? And we think that places like the Pacific border mountain ranges, the Colorado Plateau, the Basin and Range, and the Cascade Sierras are eroding faster, or we show that they're eroding faster than the Appalachian Mountains, Appalachian Highlands, and the Appalachian Piedmont. Another way to look at it is the other way. So if all the mountains in the US were eroding at the same rate, so if we control that part, everyone is eroding at 100 meters per million year, which mountains are going to be steeper? And what we see is that the older mountain ranges have to be steeper at the same rate of erosion. So if you wanted to erode at the same rate, the Appalachians have to get steeper than the mountains on the western part of the US. And this is kind of interesting, and I'm going to discuss a little bit at the end why. So what is driving the variations in erodibility? We have some speculation here, but there might be other factors affecting it, but we think that it might be something to do with rock fractures, that formed during tectonic deformation and have weakened a lot of these younger rocks more recently and made them more erodible. In older mountain ranges, they have either already eroded through their highly fractured crust, or they haven't had active deformation in a while, so some of those fractures may have healed, or simply they may have never been fractured. So maybe what we're seeing, if we go from the Pacific border mountain ranges to the Appalachian older mountains, is that we're eroding a highly fractured crustal stratigraphy here, and maybe in the Appalachian mountains we're eroding either basement that hasn't gone through the so much brittle deformation, or older rocks that don't have a lot of fractures. And as an analog, there is this older toy game that one of my co-authors said that he had when he was younger, and it's basically a little toy, and you play to be like Michelangelo, and so you have a chisel and a hammer, and the idea is that there is this cast that is pretty weak, and you can erode it relatively easily, and then you expose the harder rock of the toy. So maybe what we're seeing is something like this. So if we plot again our data of erosion rate versus the steepness, maybe we're changing from older origins that are harder, exposing that core, and in the younger mountain ranges we're still playing with that more erodible surface. Now, I think that there are several implications of this study. I think there is a lot of work to do to actually go to the details in more outcrops, like those papers by Neely et al. And others. So study more at an outcrop scale and test these hypotheses at a local scale. I just spent 4 days with Adolf Yonke and Liz Balgord throughout Utah and some students, and it was amazing to see the detailed work that they do at each outcrop, to see these very local geological features, and so I think there is an opportunity to test some of these hypotheses at a local scale. And maybe a bigger picture implication could be to think about this problem of why do we have high topography in older, relatively inactive orogenies, like the ones I showed at the beginning, or places like the Appalachian Mountains. Why are these orogenies still high? And there is other factors that affect that. So maybe we have a large crust that hasn't been eroded enough, and we still have a lot of topography due to that. There are several ideas. There is tectonic rejuvenation of these areas. So there has been recent uplift in the Miocene. But with this data, I think we can also propose a hypothesis, and is that these rocks might be harder, maybe due to fractures, but they have a lower erodibility. They are harder to erode than the rocks in the western mountain ranges. So even if they are eroding at 10 to 30 meters per million year, that is much slower than the mountains on the west, can be eroding at 300 or 500 meters per million year, so 10 times less. But even to erode at this low erosion rate, you need to steepen a lot, or in order for these mountains that are so hard to erode, they need to steepen a lot. And maybe this is what is still holding partially that high topography in some of those areas. They need to be high in order to erode. The rivers need to be steep in order to erode, even at these pretty low erosion rates. So old orogenies with low erosion rates will have higher steepness and relief than expected. And again, this is kind of what this graph is showing, that the basin steepness at a mean erosion rate is higher for these older orogens like the Appalachian Mountains. And again, going back to those landscape evolution models, now we can run these pretty big models of the world to track where we have erosion in blue and where we have deposition or sedimentation in orange. Maybe we'll have to integrate a time component of erodibility into these landscape evolution models, and also a spatial component. So mountain ranges and active mountain ranges might be easier to erode than older mountain ranges, and this might help us understand other questions of why do we get high sedimentation rates or high erosion rates during different periods of Earth's history. And this is all I have for today. Thank you very much.